Welcome, ladies and gentlemen. My name is Brian McLogan, and what I'd like to do today is just kind of work through some notes that I covered with my students on inverses of functions. So this was the last lesson that we taught for our function unit, and so I just want to kind of work through the answer key, and while I'm working through the answer key, I'll obviously be providing a little commentary that hopefully will help you out in your own classes if you are covering the inverses of functions. So we're just going to cover, we're going to learn how to find the inverse, how to talk about the domain and range, as well as how to prove that two functions are inverses of one another. To get started though, I kind of wanted to remind students on how to solve equations, and it was kind of interesting seeing how some students kind of forgot a lot about this. But the main thing that we covered was using our inverse operations, reverse order of operations, and properties of equality. In this first example, I made sure that I showed students that we can also write our equation like that, or we could apply the reflexive property. We could also distribute that 3 into both terms. So we'd have y is over 3 plus 1/3. We could also rewrite that 1/3 out in, or we could rewrite this as a 1/3 y plus 1/3, or we could actually factor that out. And I just kind of spent a little time with that just because a lot of students, sometimes when we're doing multiple choice problems, will get stuck and they'll get this as their answer and they won't realize they have the right answer available to them. They just don't know what it is. So I kind of spent a little time on there. But really the main thing I wanted to discuss with students was, again, the importance of getting rid of your parentheses. We can't use our same operation here because that 1 is inside of the parenthesis. So when we're solving for x, and actually I forgot to mention this, one thing I talked to them was, we're looking for x is equal to something, it doesn't have to be 0, or something is equal to x, right? But x is isolated. So we need to get rid of these parentheses, and I showed them 2 ways we could do that. The easy way would just be to divide by 3 on both sides. So if you just divide by 3, then you undo the division of that x, you undo the multiplication of that 3, right? Because that parenthesis is there because 3 times x minus 1. And the one thing we don't want to do is just drop the parentheses, right? You just don't want to say, I don't like parentheses, I'm just going to not use them. Well, because that is completely different, right? Then those are not the same. The y equals 3x minus 1 is not the same as y equals 3 times x minus 1. The other thing we could do is distribute that 3. So multiply the x. Let's put that back in parentheses. Distribute that. So therefore we'd have y equals a 3x minus 3. And now we could go ahead and use our inverse operations. So add 3. Y plus 3 is equal to 3. X. And then again, kind of using the understanding that I talked about in that first example, you can see that those are equivalent. Oops, I forgot to add 1. So even though they don't look the same, they are exactly the same because you could combine these or you could distribute the 3 many different ways. However, one last thing though is I want to see, well, what's the purpose of these parentheses? Because a lot of times we'll get to a math problem, we'll see, we'll have parentheses and people get stuck. Well, the purpose of these parentheses was to keep 3 times that, right? But here we're not multiplying anything, so we can just drop the parentheses. And by dropping the parentheses, we know we can just solve this now just the way we did. So it's the same operations we did in the first example. I just wanted to make sure, show people a couple different ways when we're using parentheses, how to get rid of them. And then also to remember, if there's actually not a purpose of the parentheses, we can just drop them. So then we did the same thing working with quadratic or equations that were quadratics, kind of noticing how the parentheses change. Each one of these problems is different based on what our grouping symbol that we are, or not the grouping symbol we're using, but what they are grouping. So, and then we also need to discuss the inverse operation. So the inverse operation of squaring is obviously going to be the square root. So you're going to square root both sides, but it's very important that I introduced the square root, because if I gave an equation x squared minus 4, you got to be careful because -2 is equal to -2 squared is equal to 4, and +2 is equal to 4. So we don't want to take the square root of both sides and say x is equal to +2. What we have to do is we have to include plus or minus. So whenever we introduce the square root, we have to make sure we include plus or minus. And now I've already done these operations, add the 1, divide by 3. So therefore, I'm just going to go ahead and write the answer. Now, I will write this answer like this, first of all, because a lot of my students got confused by this. But typically, guys, we don't like to write anything after the radical because then it could be confused with it being under the radical. So a preferred method here would be like that. And again, you could throw the x in front as a multiplication or something like that. Over here, now since we have our two terms are separated by multiplication, we can actually, it doesn't matter if you take the square root of both sides or if you divide by there first. However, I would kind of say that in this purpose, I can't take the square root of 3, so why don't I just get rid of it? And typically the way that I teach in my class anyways is, the easiest thing to do in most cases, just to isolate whatever is being squared. So you have x minus 1 is being squared. Just get rid of anything that's on that side and then go ahead and take the square root. So now I'm going to have plus or minus the square root of y over 3 is equal to x minus 1, and then I can add a 1 now to the other side. So 1 plus or minus the square root of y over 3 equals x. And then in this example, now this one's very important to make sure you add the 1, because if you take the square root, you cannot distribute the square root across addition and subtraction. See, across multiplication you could, so that's why it didn't really matter. But across addition and subtraction, you cannot distribute the square root. So you definitely need to get that 1 over to the other side. Now we'll go ahead and take the square root. And therefore we'll have plus or minus the square root of y plus 1 is equal to 3x. And you divide by 3, divide by 3. And again, you could write it like that, or, just remember you could also put that divide by 3 like that. Okay. All right, then we went ahead and said, well, let's go ahead and do the same thing now with radicals. Well, if the inverse operation of squaring is the square root, well, then the inverse operation of the square root is going to be to square. Here, my square root is isolated, so I'm just going to square both sides. So squared equals 3x minus 1. Hopefully you kind of got the idea here. This would be a y squared plus 1 over 3 equals x. Again, the same thing, by using this exponent here of 2, or the power of 2, we could distribute it in either case, but I just prefer to get this over to by itself, to isolate it. Now I can go ahead and square. And then typically, you don't have to, but if you were to write that in a simplified form, it'd be y squared over 9 equals x minus 1, and then we could just write that as y squared over 9 plus 1 equals x. All right, but again, same thing. Here's the problem that a lot of students do. If they square this, then you have to apply distributive property. Like that 2 does not distribute across there. So that's why it's very important to add that 1 to the other side. If you don't do that, you're definitely going to have a lot more trouble getting back into that right answer. Now I can go ahead and square both sides. So I could write this as y plus 1 squared equals 3x. Now, obviously, we don't have to square this, but sometimes if you're looking at your answer choice, I'd prefer that it's just fine just where it is. But just remember, again, let's do this. Y plus 1 squared does not equal y squared plus 1 squared. It equals y plus 1 times y plus 1. Okay? So therefore, that's going to be y squared plus 2y plus 1 is equal to 3x. Divide by 3, divide by 3. A lot of times we'll write that as a fraction in front. Doesn't have to be, but you could also just write it as divided by 3. It's cool either way that way. So those are kind of the, they bounce off each other. Students are like, all right, I'm starting to get the feel of it. And then I say, all right, well, how about let's solve for equations when we have a variable in the denominator? And this is where usually students got a little thrown off. So a couple things to remember. When we're solving for x cannot be in the denominator. So therefore, we got to get it off the denominator. And one thing that we learned when solving is if you multiply by that denominator there on both sides, so you have x minus 1 in the numerator, x minus 1 in the denominator, so those technically divide out. They divide to 1. So that leaves us with x minus 1 times y is equal to 3. Now, in this last example, we're trying to solve for x, right? We have parentheses, and it's being multiplied by y. In this case, if I want to undo these parentheses, I'm just going to divide by y. And then let's add a 1. So therefore, x equals 3 over y plus 1. It's okay that y is in the denominator. I'm not solving for y. I'm solving for x in this case. So if we multiply by x minus 1 in the first example, because that's within the denominator, then hopefully it makes sense to multiply by x on this one, because it's in the denominator. So therefore, we get an xy is equal to Those divide out, so we're just left with a 3x minus y. But in this example, what you recognize is we have variables on both sides. And the one thing I brought up to students is, remember this. Remember we had 3x minus 1 equals, 2x plus 1. Like, what did you do here? And if you remember, we had to get the variables to the same side. So you subtracted, a 2x, or you subtracted a 3x on both sides. And the nice thing is that when you did that, though, they combine together, right? You could combine these now just to give you x. Okay, and then you can easily solve the problem from there. So if we follow that same train of thought by getting the variables to the same side, we run into a problem because these are not like terms. You can't combine these at all. So then we got to think, well, what other operation can we apply then to eliminate, to get this down just to be 1x? And that idea is factoring. So when I factor that out, when I factor out an x here, I get this x equals y minus 3 and divide by y minus 3. Therefore, x is equal to a negative 1 over y minus 3. And there you go. And just be careful. Again, I wanted to cover this with the other classes. That negative 1 could go up top, right? It could go in front. It could go in the denominator. But most likely than not, if it does go in the denominator, they'll distribute it. So just make sure you're aware that those are all equivalent forms of the same answer. A lot of times it does get tricky here on multiple choice. All right, last example here. Again, we're going to multiply by this x minus 1. So therefore I have x minus 1 times y equals 3x, right? Now again, before I want to get the x to 3x to the same side, I'm going to want to get rid of the parentheses because I didn't have parentheses on this time. But I don't want to divide by y because then my x is now going to be attached with y, and I don't really want that to happen. So what I'm going to do here is I'm actually going to distribute it. So that was something that we did in the last example, or in that warm-up. And now I can get the x's to the same side. So you can see by distributing it, I got rid of the parentheses. Oops, I'm sorry, that's a xy, isn't it? So that's an xy equals 3x. Now, let's go ahead and get the 3x to the other side. So I have an xy minus 3x minus y equals 0. Let's get the y to the other side. So I have xy minus 3x is equal to y. Now I can factor out that x. So I factor out the x. I'm left with a y minus 3 is equal to y. And then you'll divide by y minus 3. So therefore, you're left with a x is equal to a y over y minus 3. Boom. And there you go. So that was what we do when we have variables in the denominator, and that will become very important when we get to our problems here. But before we get to that, the next thing we want to do is talk about what the relationship is between a function and its inverse. So I needed to get the algebra done with the students because a lot of students, have trouble in this chapter just with the algebra alone. So I want to do that before we discussed, what the graphs look like. But now let's go ahead and take a look at the graphs so we can kind of see, what exactly is going on. Okay, so basically what I looked at with the students is I gave them kind of these graphs and I just said, what do you guys know about, what do you guys, recognize the characteristics of these two graphs? And I didn't give them equations, but I told them, one is a function and one is the inverse of the function. And then I said, what about these two graphs? What does that relationship look like? What about these two graphs? Or do you guys recognize anything? And usually most people, the one thing that they all basically came across was that they had a line of reflection, which is the y is equal to x line. So I showed them that, yep, so you are correct. That is the line of reflection, which is the y equals x line. But then I wanted to probe them a little bit more. And some classes came up with it, some classes did not. So a lot of times I need to give them a hint. And I said, well, what if let's look at some of these points that is on this graph. So I selected some of the points, all right? And then it became pretty obvious to them that, oh, the x's and the y's are swapped. They're flipped, they're switched. And that's true, right? You can see how these coordinate points are flipped for each one of these functions. And what's more important about that is not even so much about those points, all right, but, we've talked about the set of values, for the x values would be the domain. You can see the domain of the blue graph is the range of the red graph. And the domain of the red graph is the range of the blue graph. So you can see that swapping of variables also helped us understand that a function and its inverse have a domain and range that's swapped. And that's something that we're going to be using, later on in the chapter. And then we also talked about, well, what about, and then I said, what about this function? And this function in its inverse, what is going wrong here? So then we went to example number 4. And I said, all right, so in this one, obviously, we have one of them as a function and one of them is the inverse of a function, but there's an issue, what is the issue? And most students figured out that, oh, well, we have something that's not a function. That black graph does not pass the vertical line test. It is not a function. And that's absolutely true. So that's an issue, right? If you're trying to find a function, and we're in the chapter of functions, and when you find the inverse, you get something that's not a function, that's a problem. So what we talked about is, have we learned anything up to this point that would restrict that? And yeah, we talked about domain restrictions in terms of piecewise functions. So I said, is there a way we can maybe restrict the domain of that purple graph so therefore its inverse is still going to be a function? And what I did was I added the restrictions of only x values that are greater than 0, right? So you can see how the green graph is only the positive version of that purple graph. And then when you reflect that, you now get a purple graph that is a function. So we are also going to be applying restrictions, but I wanted students to visually kind of see the graphs. So let's go and get into the notes here now and going in from there. Okay, so now I'm just kind of going through some formal notes, making sure we understand that the reason why that V-shaped graph didn't work is because it's not one-to-one. It doesn't pass the horizontal line test. And then we also talked about some, notation being like f inverse of x, and also for equations, just to use like y inverse. And because again, it all depends on that. Also that the function and its inverse are reflected about the y equals x line, and all those points are swapped. The domain and range, how they are swapped from one another, and how we can easily find one if given another. And then the process to go ahead and find one. We didn't really discuss this here in this class, and we're not going to work through them. But if we needed to figure out the domain or range of a function graphically, we just reflect the y equals x line, or we would swap the x and the y coordinates. But really the process that we wanted to work with was the algebraic process. And the algebraic process is given a function in f of x notation, then if it's given in function notation, then basically to make math easy is just to swap it with y. All right, because then what we're going to do is we're going to swap the x and the y variable, which makes sense because you saw graphically we swapped the x and y coordinates, when looking at those graphs, the function graph and the inverse graph. Then once you swap the variables, you just solve for y. And then go ahead and replace it back with its original notation, y inverse, or f inverse of x if you're using function notation originally. But it's fairly basic in general, but then obviously we're going to get into some problems that are a little bit more advanced. The last thing I wanted to also show is, some of the questions we might ask is to prove inverses, to prove a function and its inverse are inverses of each other. So rather than solving the inverse, we're going to use composition. So we're going to take the function, or the inverse function, and plug it into the original function, as well as take the original function and plug it into the inverse. So that was one other thing that I wanted to, discuss with the students, so therefore they could understand that as to either check their answer, or also if I ask that question, kind of directly. All right, so the next one we worked into was finding the inverse, the domain, and the range. Now, I kind of got quick to the point here. We don't really need to worry about the inverse or the domain and the range here, because one thing you recognize is that's a linear equation, that's a linear equation. Domain and range is all real numbers. So it doesn't matter. The inverse, like you swap all real numbers and swap all real numbers, you're still going to have all real numbers. The same thing for the cubic property and the cube root property. The domain and range is all real numbers. So it's not going to matter if the domain and range is swapped. So really, we just need to focus on using the notation. All right, so let's go ahead and get through that. So here we just have an equation set to y. So all I'm going to do is swap my x and my y variable, and then solve for y. So this is kind of the same thing we did in the warm-up. Instead of solving for x, though, we're solving for y. But the process, as hopefully you can see, is exactly the same. So I have x minus 1 over negative 2 is equal to y, and then I'm just going to use my inverse notation. For the next one, I'm going to replace f of x with y, and then I'll swap the variables. So x equals 3/2 y minus 2. Add the 2 to both sides. Now in this case, it's kind of important to remember how do we get rid of, oops, How do we get rid of multiplying by a fraction? Well, we multiply by the reciprocal, right? You could divide by 3/2, but that's the same thing as multiplying by the reciprocal. And just remember when you're multiplying an expression here, this x and the 2, you've got to insert the parentheses. So make sure you put the parentheses on the outside there. So therefore, we have a 3y times x plus 2. Instead of leaving this as y, that's not what the equation is. It was f of x. And again, rather than rewriting these, using the reflex property, I'm just going to leave it in this notation. But you can see how I'm leaving these, like, oops. You can see how I'm just leaving this in that notation because I know it's equivalent. There's many, many different equivalent forms. You could multiply it through. You don't have to, right? It's really just kind of all dependent. I could divide this -2 out, or I could just leave it as that. It's fine. All right, so then we do the next one. Now this one's cubed. So again, I will subtract a 1 here. So I have y minus 1 equals the x minus 2 cube, right? Because I don't want to undo cubing by using the cube root with that 1 there. Now I can do the inverse operation of cubing, which will be the cube root. Notice that when I only talked about introducing the square root, or it's really for any even root, you have to use plus or minus. So you don't have to worry about the plus or minus for an odd index. And then I'll just add the 2. Oops, I forgot to swap the variables, didn't I? So let's just make sure you do that. Sometimes you don't really need to swap the variables. We just use the swapping of the variables as one to make sense of what we're doing and why we're doing it. But as long as you kind of go back and use the same notation, you're just solving for x and then rewriting the equation. But, typically that just becomes a little bit of complicated for students, not to do that. But, as long as you understand what you're doing, that's fine. I had a couple students that were doing that in there. And you could write the 2 in front or you could write the 2 behind, right? There's multiple different ways you can look at this. Let's rewrite this as a y. To get rid of that, I'm going to cube. Okay, so I have y cubed is equal to, that gives me a -1/4 x. To undo the -1/4 x, I'm going to multiply by -4. So therefore, it's a -4. Why do I keep on forgetting to swap the variables? Jeez. I think it's just helpful to do that, though, just so then you can just replace them with the correct notation. So therefore, that becomes y, and then I will swap the y in for g inverse of x. Right? It's very important to for students to understand we're not solving for y inverse. We just used y to make the math easier. In the same respect, same thing, you don't really need to swap the variables. You just need to, but we swap the variables to, again, use it as a tool to help us find the inverse function. So, but the main thing, as long as you get back that equation and you understand what you're doing, then that's fine. All right, and then I asked the students to, once they did this, since the domain range was kind of easy for this one, I said, all right, let's pick an answer and let's actually prove it to make sure we did our answer right. So the problem I worked with them was this first example, y equals -2x plus 1. So y is equal to a -2x plus 1. And then the y inverse function, which we figured out, which we solved to be x minus 1 divided by -2. Okay, so again, if these are going to be functions of each other, then what that means is y inverse is going to be equal to y inverse compose y. Basically meaning if you plug one function into the other and the other function into the other, then they're going to always equal exactly each other. So let's go and see what exactly that's going to look like. So if I take the y inverse and I plug that in, so if I take y inverse and I plug it into that equation, so that'd be a -2 times big parentheses all right, so that's taking the y inverse function, plugging it into there. Now let's take this equation and plug it into the y inverse function. -2x plus 1 minus 1 divided by -2. All right, now I don't want to simplify, or I don't need to simplify or distribute this. You notice that if you're multiplying by -2 and dividing by -2, those are just going to divide out. So that's going to leave me with an x minus 1 plus 1 Well, x minus 1 plus 1 is just going to give you to an x. Over here, we recognize there's no real reason for us to have these parentheses, so I can just get rid of them. And by getting rid of them, I can see that add 1 minus 1 goes to 0. So I'm left with a negative 2x over negative 2, which leaves into an x. So therefore, you can see that they both equal the identity elements, and they are equal to each other. So therefore, I did my work correct. All right, then I brought up the next one is the inverses with restrictions. So what I did is I asked students, determine the inverse of the functions and kind of see where there's an issue. So a couple things, to understand why there's an issue with this is, let's go ahead and just graph what y minus 4x would look like. Well, y equals 4 minus x is the same thing as, I told students to rewrite that as a negative x plus 4. Then factor out the negative, so that's an x minus 4. All right, so that means that's reflected about the y-axis and shifted 4 units to the right. 1, 2, 3, 4. Okay, now we know what this graph when this graph is going to have a inverse, it's going to be reflected about that line. So now let's go ahead and figure out what exactly is this inverse here that we are working with. So, we'll replace it with y, swap the x and y. So we have x is equal to the square root of 4 minus y. We're going to square both sides. That'll be leaving with the x squared is equal to 4 minus y. And then when you go ahead and solve for y, you subtract a 4 on both sides. X squared minus 4 equals to a negative y. And then you divide by negative 1. And you get y. You put the y to the other side, so you can see that's a negative x squared plus 4. Now, we should know what that graph looks like. That is a quadratic graph. And by looking at that quadratic graph, you can see that that graph is shifted, 1, 2, 3, 4. So that graph's going to look something like this, right? And hopefully immediately you recognize this and say, that blue graph is not the inverse of that red graph, right? That is not reflected about the y equals x line. So therefore we say, well, could we restrict it, right? Could we restrict that graph so therefore it is? Can we look at the, one side of the graph and it would produce the exact same reflection? And the answer is yes. If we actually restrict the graph to only be the positive version of the graph, you can see that now it creates a restriction. So once we get our answer, we recognize though we're producing a quadratic, which is not a inverse function of the square root, and therefore we're going to restrict this for x values greater than or equal to 0. Then for the next one, kind of comes into the same thing. We recognize this as a quadratic, and obviously, guys, a quadratic is not 1-to-1. So therefore, in the same idea, we have to restrict the domain. Now, hopefully we again recognize by factoring out the 2 that that graph is going to have a horizontal compression of 2 and a horizontal shift 1/2 units to the left. So the graph looks something like this. Here's 1. Here's negative 1, or here's negative 1, I'm sorry. So that would be like negative 1/2. Right? But again, we're not using the whole graph because that wouldn't be a function, right? And therefore it wouldn't have an inverse. It wouldn't be 1-to-1. So therefore we're only going to use the version for x values less than or equal to negative 1/2. And then again, we need to figure out, well, what again exactly is this inverse here? Right? So now we just need to go ahead and do the math. So we'll swap this with y, swap the variables. So we have x is equal to 2x plus 1 squared. 2x plus y. Okay, y. Take the square root of both sides. We recognize when we take the square root, we have to include plus or minus. But it doesn't make sense for us to include plus or minus, actually, if you think about it. Because 2y plus 1. Because think about it this way. If you have, if here's a graph, right? If this represents the square root of x, this represents negative square root of x. Well, positive square root of x and negative square root of x, if you include both of them, you're not going to have a function anymore. So we have to pick one of them. Which of these graphs, either the positive version or the negative version, looks like it's more likely going to resemble the reflection of this graph? If you flip this graph over, you can see that it's more going to resemble the negative version. So when we're given this inverse, we recognize we're actually only going to take the left or the negative version of that square root, which is going to leave me with a 2y plus 1. And if you solve this a little bit more, you can kind of see how that works. But negative square root of x, oops, I got to go back and write that answer. I forgot to write f inverse. Oops. Sorry, I just thought about this. I was like, oh, I got to write the answer here. Okay, and this would be minus 1 divided by 2. And if you simplify that a little bit more, that's f inverse again. Okay, if you simplify that a little bit more, you recognize that that is actually a square root function with a little bit of a vertical compression here, but actually a shift downward. And you can see as I graph this, that negative version, right, you can see that graph works. And a lot of students have trouble, like, how do I know which restriction is which? It helps just really know these graphs. Obviously, when you're using the left side of the quadratic, you know that the reflection is going to be the negative version. If you're restricting the right side of the quadratic, you can think of the positive square root. So then I went ahead and just kind of gave them, 4 examples to try with those restrictions. So, all right, on those restrictions, again, the same idea, really quickly. We know what this graph looks like. Let's go ahead, hopefully we recognize that it's 2 units to the right. So, therefore, when I reflect this, I'm only going to want the positive version of my quadratic. So, x is equal to negative 1/2, y minus 2. Let's multiply by negative 2 here on both sides. So that becomes a negative 2x equals the square root of y minus 2. Let's square both sides. So that becomes a positive 4x squared equals y minus 2. And then let's use this as inverse operation. So you can see I'm just kind of doing a little bit more work a little bit faster now because we've already spent so much time using our inverse operations. However, again, I only need to use this positive version. It doesn't make sense for me to see the negative version as the inverse, as that reflection, right? So we're just going to say x has to be greater than or equal to 0. All right, so let's go and do another one here. So now this one is going to have a shifted up 3, and then the graph looks like that. So again, if I reflect this, you can see that this as a reflection about there looks like it's going to be that right-hand version. You're not going to want to use the left-hand version, so that'd be like right there actually, right? Because you're going to get a quadratic, but you can see how the right-hand version is going to better resemble this than the left-hand version. And again, oh wait, I forgot to do this. Oh no, I made a mistake. My bad, crap. This was a negative. I forgot that, so I graphed that wrong. So let's fix this. So now it's actually a reflection about the y-axis. So you can see how that doesn't work as a reflection. But if you use the negative version there, you can see how that would be the reflection. So I wasn't paying attention. And actually, all we got to do, though, to make this a little bit easier, is just flip that. Okay? But now, hopefully by understanding this graph, we can see that we're going to use this positive version. We just need to figure out what that reciprocal is. So I'm just going to replace this as a x. The square root of 2y plus 3. So we have x minus 3 equals square root of 2y. Square both sides. And then I'll just write that as f inverse equals 1/2 times x minus 3 squared. Okay, and then obviously you can see that the graph is being shifted 3 units to the right. However, we want the positive version, right? So we want to represent values to the right of the vertex, which is at 3, 0. So a big mistake students will make here is that they'll do like x is greater than 0 because they're so used to like the vertex being at 0. But again, the vertex can be over and it's not at 0, it's at 3. And we want the positive versions. The negative versions would be x is less than or equal to 3. And let's just put an x there. All right, now let's get into the squared ones. Well, now obviously these ones have a, what did I change? This one, I think this one was supposed to be x is less than 0. And this one was x is greater than or equal to -1. Yeah, that's right. And I forgot to do this one. So That was supposed to be changed, x is less than 0. So what that means is, if again, this graph, 1, 2, 3, I'm just using the left-hand side. So I got to think when I reflect this, am I going to use a negative graph or a positive graph? And hopefully look at this, we can recognize that the reflection here is going to be a negative graph, actually. Graphing like that as like a reflection. But let's just go and take a look. Like the positive reflection is not really like, that wouldn't really work, right, if you reflected that. But let's go and see. So swap the x and the y's. So we have x is equal to y squared minus 3. All right, add 3. So we have x plus 3 is equal to y squared. And then we have y inverse is going to equal, plus or minus the square root of x plus 3. Okay, and again, you're either dealing with the positive version, which does not look like the reflection, or the negative version. And we can see that the answer is going to be the negative version. And again, you can see that since x is less than 0, since we're using the left-hand side of the quadratic, we're going to use the negative version. So my final answer, y inverse, is going to be negative square root of x plus 3. So then maybe we can probably assume that the positive version here, we're going to use the positive version. This graph is a little bit more advanced here. Let's see, it's being shifted left 1, down 1. It's being opening down and has a vertical compression of, vertical stretch of 3, and it's only for x values greater than 1. So the graph looks something like this. So if I'm going to reflect this about the y equals x line, I got to figure out, am I going to be using a positive version of the x or a negative version, right? It kind of gets a little crazy here what this looks like. So let's go ahead and swap the variables and actually solve this one. So this one is x equals a negative 3 times y plus 1 squared minus 1. So I have an x minus 1, or x plus 1, equals negative 3 times y plus 1 squared, divide by negative 3. So that's going to be reflection, so that works. So therefore, it looks like that's going to be x plus 1. Let's do this as a negative 1/3 equals a y plus 1 squared. Let's square root. So now I'm going to have, let's see, g inverse of x is equal to a plus or minus the square root of negative 1/3 times x plus 1 and then minus 1. So now we know that the horizontal stretch is being shifted 1 unit to the left and 1 unit down, right? And it's reflecting opening out down this way. So we could either use the positive version or we could use the negative version. And hopefully you recognize that the positive version of that square root of x is going to work. So therefore, I am just going to erase the negative version and leave it as positive. And you don't really need to keep the positive there. You could just leave it as is. But that's what we wanted to kind of talk with as far as in terms of the restrictions, because not only is that kind of difficult because you really need to know what the graph looks like, but also we need to understand the domain and range. Now, one thing I kind of forgot to mention, I forgot to do the domain and range for these. My apologies. But I think if you know what the graph is, you can figure out the domain and range. Like, you don't need to know the inverse or the domain. You don't need to know the domain of the inverse graph to find the range of the function, right? But you could do that. And so hopefully you see from this graph here, the domain is going to be all numbers from 2 to infinity. The range here is going to be from negative infinity to 0. Now, if you notice, that is defined here in that domain restriction, negative infinity to 0, right? The domain of the inverse is the range of the function. Again, let's look at another one. Here, this is my original, or that's my original graph. So the domain here is 0 to infinity. And my range in this case is going to be 3 to infinity. And if you look at this, again, the domain of the inverse function is 3 to infinity, which would be the range of my function. But I think, the way that I teach these is knowing what these graphs are. You don't have to rely on knowing what the range is to be able to figure it out, because, sometimes a lot of students don't know what, that graph is going to look like or what the range is of that graph, like particularly like this example. Students have to, there's a little bit of manipulation you have to do to really understand what that graph looks like, to understand that that's 1/2 unit down. Okay, so sometimes people aren't as comfortable with that. So that's why I always recommend making sure you can find the domain and range from the original function based by just knowing the graph. Now, the nice thing about when you're given a function with a domain restriction is the domain is the domain restriction. The domain here is all real numbers less than 0, right? And now I just need to figure out the range, which is the domain of this, but let's just look at the graph. That was my graph. The range looks like it's going to be from -infinity to -3. Oh, I'm sorry, to 0. There you go. And the domain of this one is, again, my domain restriction. So that's going to be from -1 to infinity. And my range is -infinity to -1. Okay, now I wanted to cover that because the last thing that we're going to cover is finding the inverse of rational functions. And the problem is, we haven't discussed what these graphs look like. So we know what the domain is. The domain for these is rather simple. We know that domain is all real numbers except for the numbers that make my denominator 0. But as far as understanding the range, that's not as clean cut. I'll get to that one later. So what we need to do then, here we really need to rely on understanding the domain of the inverse. But first, to do that, we got to figure out the inverse. So let's go ahead and do that. So we have x is equal to 2 over y minus 3. All right. Then just like our warm-up, we're going to multiply by y minus 3 on both sides. And then we have y minus 3 times x equals 2. In this case, just to solve for y, I'm just going to divide by x. And therefore I have y minus 3 is equal to 2 over x, and then I'll add a 3. So I can say y inverse is equal to 2 over x plus 3. And then you can say, all right, so what is the domain here of this inverse? Well, the domain of this function is all real numbers except for 0, right? That's the only number that makes my denominator equal to 0. So the nice thing about this is that's the range of my original function, right? So now when I go back to say what's the range, I just go to the domain of my inverse. Now I got to make sure that I write this back in the correct notation, which I did. So cool. All right, so let's go and do the next example here. Now this example, we know that domain here is all real numbers except for 0. Okay, so let's go ahead and figure out the range. So we'll swap this with y. And then we have x equals y plus 1 over 2y. All right, multiply the 2y on both sides. So we have a 2yx equals y plus 1. In this case, we're going to want to factor out this y. So we have 2yx minus y is equal to 1. Factor out the y. We're left with a 2x minus 1 equals 1. Divide by 2x minus 1. Divide by 2x minus 1. And therefore, we can say f inverse of x is equal to 1 over 2x minus 1. And if you set your denominator equal to 0 to figure out the values that are not in the domain, you would see that's x equals 1/2. So the range in this case is going to be a -infinity to -1/2 union -1/2 to infinity. All right, so you can see how understanding the domain and range is swapped is really, really important for these rational functions, unless you know what the graph looks like. And we don't deal with calculators in my class, so that's why we, oh, I forgot to change those over. So that's why it's very important. So let's go and do these last two examples. I guess I switched around my slides. All right, so last two examples, same thing here. We can figure out the domain. So let's set 3x plus 6 equal to 0. Say x is equal to 2. So say my domain here is all real numbers except for 2. All right, so now let's go ahead and swap the x and the y's. So x is equal to y over 3y plus 6. Multiply by the 3y plus 6 on both sides. Now in this case, I don't want to divide here to solve for y. I don't want to divide by x, so I'm going to need to distribute. So here I have a 3yx plus 6x equals y. And now I get the y's to the same side. So I will subtract a y on both sides, and I'm going to subtract a 6x on both sides. So therefore, now it's going to contain a 3yx minus y equals a -6x. Factor out the y. So that's a 3x minus 1 equals a -6x. And then divide, and you will get y inverse is equal to a negative 6x divided by 3x minus 1. So there, hopefully, if you were understanding the domain of this one, it would be all real numbers except for a positive 1/3. So therefore, again, the domain of the range of inverse is the range of my function. Okay, last but not least, guys, the last problem. Yay. Let's go ahead and do the domain real quick. Domain's all real numbers except for 1. All right, swap the variables here. So we get x is equal to 2y plus 1 over y minus 1. Multiply y minus 1 on both sides. Distribute. Don't see what happens when I start skipping out on my work. So you distribute the x. Now, let's go ahead and get the y's to the same side. Let's add the x here. So now I have a xy minus 2y is equal to a x plus 1. Just rewrite those. Factor out the y. So I'm left with an x minus 2 is equal to an x plus 1. Divide by an x minus 2. Divide by an x minus 2. And therefore, we can say that g prime of x is equal to an x plus 1 over an x minus 2. And therefore, I can identify now that the domain of that function is all real numbers except for 2. So therefore, the range of my function is going to be all real numbers except for 2. And that, ladies and gentlemen, is how you find the inverse of a function for rational, radical, as well as quadratic using restrictions for the cubic, cube root, and linear. Last thing, I just had students write down some reflections, what they understood, what they had trouble with. If this is something you're learning for the first time or just for a second time, and if you had anything you'd like to add as far as some, still some points maybe that I wasn't clear or didn't clarify, then please feel free just to go ahead and comment down below, and I'll be more than happy to hear your responses and help you out as best I can. But this was a full lesson that we did with the students, and I hope it helped you out any way that it could. So cheers. I'll see you guys on the next video.